in a meeting where we have heard frontier talks, and we'll also be carrying on the dialogue on gender equity. So what I'll do today is briefly talk about what have we learned from JWST about the early phase of star formation. Vasudev talked about massive stars. I'll restrict myself to low mass stars. They are relatively easier to study. Massive stars are more complicated. And I'll also briefly, last two slides, I'll briefly mention, talk about how men can be allies in the struggle for gender equity. So when the stars form, after the initial gravitational collapse, you arrive at this configuration where you have a central protostar, a disk around it, and a collapsing envelope from which the material is freely falling onto the disk. This is not an equilibrium situation. This is a dynamical thing. The envelope is collapsing at free fall times. We call it protostar or protostellar phase. This is the earliest stage of star formation. And this is probably the most important phase. At a very fundamental level, you can look at protostellar evolution or this phase as being driven or regulated by three mass flows. The collapse of the envelope, which we call envelope infall, accretion of material from the disk onto the star, which is called disk accretion. And at this stage, somehow bipolar outflows or jets and winds breaks out, and that's the other flow, third flow. So ideally, if you can measure these mass outflows as a function of time, you would understand everything about star formation, but that's easier said than done. But JWST now is making serious inroads into one of these flows, namely jets and winds and their interaction with the envelope, and I'll briefly talk about that. But what has happened in the last decade or so, there has been a paradigm change in the way we understand accretion and jet launching. Accretion, for a long time, jets and winds in astrophysical scenarios, they are ubiquitous in astrophysics, in astrophysical objects. It's always thought that accretion drives winds and jets, which is true in the case of a supermassive black hole or black X-ray binaries, where the compact objects are the central gravitating object, and there the accretion disk is entirely ionized, and the magnetorotational stability can provide the turbulent viscosity needed to accrete material onto the disk. But here we are talking about a predominantly molecular disk. There is only very little ionization in the surface of the disk. And it has been shown that that is not enough to explain some of the accretion rates that we measure in these stars. So the new paradigm is that the winds and jets are not some peripheral phenomena in formation of young stars, but they are the drivers. They make accretion possible. Stars form because of magnetized winds and jets, and that is what I want to talk about today. And one of the prediction of this magnetized winds or the disk winds has been that they follow this radially stratified thing. The velocity is fastest in the center, and then it's slower outwards. And JWST studies appear to confirm this, and this is what I want to show you today. This is an IRCAM image of a jet driven by a young star. Young star is over here. You can't see it. It's so deeply embedded that the extinction is so high. And this is what you're seeing, this emission in the rotational transition of hydrogen, the pure rotational transition of hydrogen. It's a line emission. This field is about 2 arc-minute in size. But what I'm going to show you, the results are entirely based on the NIRSPEC and MIRI spectral images, IFU spectral images of JWST. And we are looking at the central white box. And these are the results. I've listed down the results, and in the remaining slides, I'm going to demonstrate it to you that this is indeed the case, how we have arrived at this result. The first result, the flow structure that we detect is nested, onion-like, or stratified in morphology, velocity, and excitation. I'll explain to you in a minute what that means. One of the most important discovery that JWST made, the discovery of wide-angle molecular wind driven by traced by hot, fast-moving molecular hydrogen gas. This, what it shows is that the material is being driven from the disk. It's not some entrained material. So this is really new, and this has been the major contribution of JWST. And this molecular winds, the wide-angle molecular winds, seem to be the dynamically dominant component, not the collimated jet that you see. So let me first explain to you what do I mean by this onion-like nested structure. So this is the collimated jet, often traced in fine structure lines, forbidden iron to, this is the brightest line, I'm showing you this, but in neon to argon, singly ionized argon, and various fine structure lines. So you see extremely collimated. By highly collimated, I mean opening angle is less than 5 to 6 degree. This opening angle, half opening angle, is less than 5 to 6 degree. And they are moving fast. Inclination corrected velocity is in excess of 150 kilometers per second. Clearly telling you that it's escaping from the gravitational well of the gravitating body. So this is the innermost part in the fine structure. And then in the outer wide angle, you have this molecular hydrogen jets. These are seen in the pure rotational transitions of hydrogen in the ground vibrational state. S1 is the transition from rotational level J3 to J1. And S5 is the transition from rotational level S7 to S5. Delta J is 2 here because hydrogen doesn't have a permanent dipole moment, so it's quadrupole transition. What you see is the lowest excitation transition, the opening angle is much larger, 35 degree or so. But when you go to higher and higher excitation, it's becoming narrower and also faster. So typically, so here in the S1, the lower excitation, the velocity is 10, 20 kilometers per second. By the time you reach to S11 or so, it becomes 40, 50 kilometers per second. It's demonstrated here better here. From S1, it's wide angle, slow moving. When you go to S5, S6, by the time you reach S14, and it's becoming extremely narrow and fast, 50, 60 kilometers per second. So this is the nested structure that we are talking about. This is a direct prediction of the magnetized disk wind model. How about the physical conditions? So what we do is from an aperture like the central aperture, the cyan one, we extract the lines and we construct what is known as a rotational diagram. This is just the Boltzmann equation of level population. You take the natural logarithm of it, plot the y-axis is the natural logarithm of column density. So so you know Ni by n, n1 by n2 is equal to g1 by g2 e to the power. So if you take natural logarithm, there's a x-axis u by k, and the slope of the straight line fit. If it isn't perfect in a single temperature component, it will be fit by a straight line, and the inverse of the slope will give you temperature. But clearly, it cannot be fit by a single straight line. We chose to fit it by 2 temperature component. What it really means is there is the range of temperature, but for convenience, I'm showing you this. The warm component is 500 and the hotter component is about 2000 Kelvin. This 2000 Kelvin gas, so it's shock gas clearly. So the gas in the disk is few tenths of Kelvin. So it is being lifted and shocked internally, and that's what we are looking at in these flows. One of the interesting findings is that the temperature that we derive from that rotational diagram. So from this rotational diagram, you derive 2 things. One is temperature, which is the reciprocal of the slope, and other is the column density. That is a y-intercept. So for both warm and hot temperature, you get a column density. You know the column density, you know the emitting area, you get the total mass, hydrogen mass. Then if you also have some dynamical time, if you know the extent of the flow and the velocity of the flow, which we have, then you get a dynamical time. Divide the mass by dynamical time, you get a mass loss rate. Multiplied velocity, you get the momentum rate. So you get that's what I'm showing you here. The temperature, so we have in our particular program, we had 5 protostars spanning a luminosity of 5 orders of magnitude, 0.1 solar luminosity to 10 to the 4. The temperature or the physical condition of the hydrogen flow is remarkably similar. The temperatures are, the hot component is around 2000 and the warm component is around, which means that the physical conditions are very similar. But the column density or the dynamics, m dot, mass loss rate and momentum rate, m dot v, scale sublinearly with L bole. L bole is the protostellar luminosity, total energy out from the protostar. And this sublinearity has implications. I'll not go into that. But what was even more interesting was we measured the momentum rate in the collimated flow, which we detected in the fine structure lines, and the momentum rate or the force, outflow force in the hydrogen flow. The solid circle are the momentum rate or the outflow force in the hydrogen flow, and for each of these sources. And the crosses represent the momentum rate or the outflow force in the collimated flow. For most sources, except B335, that's a special case. It recently went into an outburst, major outburst. So there the collimated flow seemed to dominate. But in all other cases, the momentum rate of molecular hydrogen, wide-angle wind momentum rate exceeds that of highly collimated ionic jet. So it's no way that the ionic jet is driving this other flow. So this has been a new realization. And so just to summarize again, the major JWST insight is that nested onion-like stratified structure in morphology, velocity, and excitation. And the major discovery was this wide-angle, relatively slow-moving compared to the collimated wind, this wind, which is the dynamically dominant component. And for all the feedback, mechanical feedback question related to star formation, this component would be the important one to consider. Now, let me, the last 2 minutes, we talk about how men can be alive. I don't see many men in the audience, so disappointed. Yeah, so I apologize for my biological sex and gender on behalf of them. But I think men have an important role to play. I think and that's why is it? Why do we need men as allies? First and foremost, this is not just a women's issue, because equity is relational. See, inequity is because of uneven distribution of power. And for redistribution of power between genders, men need to be willing partners. Otherwise, you're not going to achieve it. So men need to be part of it. So they have to be there. And it has been shown by and large that efforts and investing in women alone will not bring progress. And the reason is, we know that institutions are male-dominated and men occupy important positions. And if they are allies, they can use their power to bring about change. So it's important that they are. And men also benefit. I mean, often people don't realize it. See, for a more equal society, it's good for everyone. And, it helps you challenge gender stereotypes, rigid gender norms, and negative masculinity. So people have to be first be aware of this, right? I mean, before you can even challenging it. So how can men be good allies? See, I'm not saying this as a prescription, I'm a great guy doing all this. I'm also struggling with all this and trying to do what best I can. So this is just some research that I have done, and I'm sharing it with you. I thought this is important to bring this out, although there are fewer men in the audience, but we need to talk about this, I think. So we need to, as men, we need to educate ourselves on gender-related issues, because it doesn't come to us naturally, because we are not the victims, we are the perpetrators. So it's harder for us to recognize the problem. So we need to spend some time on scholarly studies and look at and often it's difficult because these biases are often implicit, it's unconscious. So there are several tests online. There is one at Harvard to test your implicit bias. So I urge all of you to take it up. And I was surprised to see, how seriously affected I was of various gender stereotypes and other biases. And as an ally, I think we should learn to partner and collaborate with humility. I mean, remembering that it's not about you, not about men. You listen to women. And very importantly, share your social and academic capital and platforms like influence information. So this is very important. This is often, from my experience, men don't do this often. I think it's important to do this to create a more equitable working atmosphere. And then the most difficult part, I think, is acknowledging male privilege. I think we should probably remember that our privilege is perhaps not our fault, but it's certainly our responsibility. So we need to, and most importantly, I stress this, this cannot be stressed enough. So gender inequity is an institutional problem. So you can't expect women to rectify it. I think men need to be equally responsible for it and work towards it. So you cannot, inequity is not solely a women's responsibility. I think it's important to keep this in mind as well. So I'll stop here and take questions on either of them.
Questions? Comments? This might be a naive question, but in the end slide, you mentioned that the jets that are being produced by these low mass stars, uh, is it being studied how it affects the environment in the galaxy or wherever these stars
Yeah.
are?
So that's an important area of research because many of the simulations, the recent ones, show that mechanical feedback from these low mass jets and winds do have an effect on the overall stability of the cloud, star formation rate, etc., etc. So it's being looked at. If you want some details, we can talk about it. Yeah. It is. It's a major area of research now. It's picking up. Yeah.
Yeah, so what I'm getting from this is that now these outflows and jets are very common, and that's why this particular scenario that actually jets and outflows drive accretion and not the other way around. Is that what you're saying?
No, so it's this early. This was already happening in the last 10 years. JWST is just confirming some of the predictions, especially this radially stratified wind. This is primarily from the disk simulations. I'll send you some of the. Yeah, these two references kind of summarizes various. So it's from 2010 to 2022, or so series of papers by various simulations. The latest state of the art.
How do you see it's confirmed or something?
That I think you are the expert, Pallavi. I don't understand, but I just read this and that's the field seems to be. I mean, even your simulation field seems to be moving in that direction. So one of the issues that they're saying is okay. Even in low mass stars, your ionization is only in the surface layers and it's small. So you can have MRI in the surface, this on both upper and lower surface, and you have this midplane in there. That's a dead zone. That's where planets form. But that is in various simulations. That is not enough to explain the accretion rate that we actually observe. There's 2 orders of magnitude less the accretion rate. So you can't. So even and if you put in that is without dust. If you put in dust, then it will further go down. So there are some serious. I don't know the details of simulation because I'm not a simulation person. So, but I'd love to talk to you about this and to assess whether whether there is really an issue or to understand the simulations better. Yeah.
Thanks.
Maybe the younger people can ask first.
Okay, sure.
So just like you have been advocating for women equity. I mean, you have been studying and doing something on it. So did that affect you in your academic spaces? Were you being sidelined for that reason in this male-dominated spaces?
Much less than how it affects women, right? I mean, even if it does, I mean, it's. Okay. See, I think that has to be very clear about it. So men are okay. I think the gender thing is directed the other way. No, so okay. Yeah. So there is this. Anyway, so I think it's let's not real. Yeah. So it's. I think we shouldn't even be talking about that, whether men suffer. I mean, that's not the. I think we should not.
Because you speak about this. That's what I'm asking. Because you have been advocating for it.
I don't think. I mean, I think as Maushami was talking about in mid-90s, then it would have been different. But now the whole thing has changed. From the government now there are instructions. You have, so it's all in this going in this direction now. So the climate is now easier.
So you talked about how equality is everyone's work. One of the simple things that you could possibly add to your list is that men, at least the ones who are mid-career and up, should just refuse to participate in conferences and committees and panels if there aren't 30% women there. This is a very somewhat successful strategy outside of physics, at least. I know many friends of mine who have done that, including well-known people in Bengaluru. So I think that is something that people should do, because the onus should not be on the WGG, on the that thing to say there should not be manels, there should not be.
I think it makes a huge difference if men also start talking about it. I think things start crumbling now. This sharing the social and academic capital and platforms. I think that also is a crucial thing. It makes a huge difference, I think.
thank both our speakers once again.